Hey, what's up YouTube? So today we're going to be looking at the IR2110 MOSFET or IGBT driver. We'll be looking at a little bit why we need one, why can't we just drive this off of a microcontroller. I have the National Instruments myDAQ here. I got given that when I worked at National Instruments. So I'll use it in this just because I need something to drive it very quickly instead of using an actual microcontroller where I have to write actual C code just to speed things up. But the main point of this is to run through design exercise as to using the IR2110. Commonly these calculations are the bootstrap driver, the bootstrap capacitors that are needed, the bootstrap diode, how we can spec that out, make sure it won't fail, likewise with the capacitors. And the application I'm actually going to be aiming towards is a Tesla coil driver. So I'll be hopefully designing a Tesla coil pretty much from scratch, and I'll make videos as and when I do that. I've been playing around with the Slayer exciter circuit. It's very basic, low power, pretty temperamental circuit, so I'd like to move over to a solid state Tesla coil, which I've made before, but I did that about 4 years ago now, so hopefully I've got a few more, a little bit more knowledge on that, so we can build a better one and get some bigger sparks. So, let's go. So first of all, I'll do an explanation of what a high side driver is and why we need one. So first, I'll do an explanation of what high side driving and low side driving is. So let us imagine that we have some power supply, VCC, we have a load, R load, and we have ground. Okay, so there's 0 volts. Some current will flow through here, proportional to the resistance and the voltage. So, let's say that we want to introduce a switch right here. So we're going to put a switch in here, like that. Okay. Now we can control the current flowing through this resistor by turning this switch on and off. And this is on the low side of the switch, or low side of the power supply, and voltage that's associated to this, which makes it low side switching. Likewise, if we put a switch up here, like this, it's called high side switching. Okay, so we'll become a little bit less abstract, and we'll draw the circuit again. But this time, instead of having generic switches, we have a MOSFET. So there's a MOSFET at the top. I'll just draw the top one for now. And there's our load again, and 0 volts to ground. So, for those of you who know, this is the source of the MOSFET, drain of the MOSFET, and gate of the MOSFET. And essentially, what this does is if we apply a voltage to the gate, it will allow current to flow from the drain through to the source. Usually there's a threshold for the gate voltage, and it can be anywhere between sort of 2 to maybe 4 or 5 volts. The switch I'm using is going to be 4 volts. And I'm not actually using a MOSFET, I'm using an IGBT, and I can explain those in a minute, but for all intents and purposes the driving of them is the same. So what we're saying is we need to apply between the gate and the source a voltage of at least 4 volts. So I'll say we want to drive this at 12 volts. Okay? Now where is that 12 volts going to come from? So this is at VCC potential. And if my VCC is at 12 volts, I need to be able to put the gate here 12 volts above this point. Okay? So let's take a little look at this circuit again and assume that the switch is closed and we get this. So there's 0 volts. Up here is our 12 volts. And right here is also now 12 volts. assuming 0 voltage drop across this switch here. That means that in order for me to be 12 volts higher than the source of this MOSFET, I need to provide not 12 volts but 24 volts. And where does 24 volts come from? Usually, for applications like this, the voltage that you're switching at the top here is usually the largest one that you have on your board. If you happen to have 24 volts somewhere else on your board, that's great. You can step that down, and you can use that for your VCC, and then your 24 volts can go and be used to drive the gate. However, if you don't have that, then we need an isolated supply for this, and that's where the gate driver comes in. So if we look at the IR2110, it has a H-out output, or HO output, which goes to our MOSFET here, like that. There's the drain, there's the source, there's the gate. It has something called a VB and something called VS. Now what the function of this is you add what's called bootstrap capacitors to this. So there's one capacitor. You may have a succession of capacitors, which I'll speak about later on as to why you would do that, why that's good practice. And it also has VCC connected to it, which is usually 12 volts or 15 volts, something like that, and that's needed mainly for the functionality of the IR2110. It's got some internal circuitry in there. Well, finally, what it has as well is a diode. And this diode connects to the top of VB, and this is what provides us with the isolated 12 volt supply that we need. Okay, so if VCC is 12 volts, we have current flow through this diode into the bootstrap capacitors, and it charges up our bootstrap capacitors. Just one point, that in order to do that, we need to reference the bootstrap capacitors to the source of our high side FET. If we don't do that, there's nothing in here to allow these to charge, and they'll just sit there not charging because the base of them is floating. Okay, so it has to be tied to the source there. Generally your load is over here, so in my case it's going to be a coil or a buzzer. Really for the Tesla coil this is just going to be a few turns of wire to make a primary coil. At the moment it's just a buzzer, and then you have a low side switch here. And it's quite important that you have a low side switch for the IR2110, and I'll explain those reasons in a moment. So current is going to flow, if I get a red pen, through here, through the diode there, and it's going to start charging these capacitors up, which is great. So we'll have our isolated 12 volt supply there, but this will only charge up when the low side switch is closed. So if this is open and this is closed, current can then find a path to ground like that, and that's how it charges up, which is why it's very important to have a low side switch, because if you don't have this low side switch, then you won't be. So let's imagine that this is not here and we have our ground over there or something like that, or I don't know, something here. There won't necessarily be a path to ground for these capacitors to charge up, so that's very important. So there's the isolation that you get, the isolated supply that you get with the IR2110. Another thing that it does, which is also very important, is here this gate is isolated from your drain and source. The only thing that's, and due to the nature of isolation, you get a very small capacitor here, probably in order of picofarads, I think it is. But if we draw that little cap there, this capacitor, when initially you apply some charge to here, is a short circuit, and you get a very large current flow into this capacitor in order to charge it up. And then as the charge builds up on it, so does the voltage, and once the voltage exceeds the threshold voltage that we spoke about here, you'll turn your MOSFET on. That's basically how they work. And that's the reason to have these capacitors here, is so that you have enough charge stored that you can quickly, and that's really the key here, is you can quickly discharge that capacitor, oops, sorry, that's the wrong way, quickly discharge that capacitor through H out to the gate here and turn this on as quick as you can. If you turn it on very, very slowly, so you can either turn, let's go to a new page. You can either turn your MOSFET on very slowly, like this, and you'll get a very smooth transition. There won't be any ringing on it, but you'll have a lot of what's called switching losses. So when the MOSFET is switching, is really the only time that it's dissipating any heat, and so the area under this curve here, whilst it's switching on, is essentially your power loss. So the quicker you can turn this on, the better. But the downside to that is, if you're turning this on very quickly, you'll get oscillations, and that's due to the capacitive effect of the gate and the trace inductance going from the IR2110 to your inductor. Which is why on your IR2110, if I go back to that page, which is why if you're designing a PCB, this trace here that's going from the IR2110 to your MOSFET needs to be as short as it possibly can, and that reduces the inductance and will help reduce ringing that I said before. Another thing that will help the ringing is turning it on slower. The way that we can do that is with a gate resistor. But that aside, those are just a couple of things that I wanted to mention. The IR2110 has a totem pole arrangement on its within it, which is what does the switching between the bootstrap capacitors and the H out. It also has the benefit of, if this is your gate, let's just do that like that, it also has the benefit of discharging this capacitor very quickly as well. So if you imagine that we've got basically the totem pole arrangement is like this, we can either switch this output here, and this goes to the bootstrap capacitors and it can charge it up very quickly, or we can have this open and close this switch and discharge this capacitor to turn this off very quickly, because we not only want to turn it on as quick as we can, we also want to turn it off as quick as we can, because again the same thing applies. If we turn this off very slowly, then we have all this time where the MOSFET is conducting and we're going to have switching losses. So that's the reason for a driver. Two main points to take away. The first one, it provides an isolated voltage source to turn the gate on. It also provides fast turn on of the IGBT or MOSFET, which will in turn help reduce your switching losses. Now, let's actually start designing this. So the first thing we're going to look at is the MOSFET. A few things you need to consider are what load you're trying to drive. So I'm trying to drive a coil, which means that my MOSFET needs to be able to withstand the voltage that's seen across this. So if I'm providing 100 volts across here, then the MOSFET drain source needs to be able to withstand that much voltage. It also needs to provide, or to be able to provide, enough current. So your IDS, which can be found in the datasheet, needs to be sufficient enough. An example might be 8 amps. So your MOSFET can easily, or within spec, source 8 amps from its drain to source. And finally, something else you should consider is this thing called RDS on, and you'll see it probably on the first page of the datasheet. It's usually in milliohms, or sometimes they'll write it like this to make it seem smaller. So this is an example of 0.18 ohms, and that's essentially the equivalent resistance of the MOSFET once it's turned on. And you want this to be as low as possible because your power that's dissipated within the MOSFET is equivalent to your current multiplied by your RDS on value. So if this is small, power losses will be small. And if you're designing something like a DC to DC switch mode converter, then really the only losses you're usually seeing are within your MOSFET. You've got some copper losses and stuff in the inductor and stuff like that, but the MOSFET really is the sort of limiting factor at the moment, and you can get efficiencies in order of 98%. So I think the one that I made at the European Space Agency, the power stage was 97 or 98% efficient for a given load and voltage. But that aside, so those are the things you need to be considering. If another thing we need to look at is the frequency, because we need to know how fast we're switching this. That will then allow us to do the calculations for the bootstrap circuitry on the IR2110. So I'm going for 150 kilohertz. This is because for a Tesla coil they kind of resonate between 50 kilohertz and maybe 1 megahertz. The Tesla coil I'm looking at making is going to be around this figure, so hence why I'm designing it for that. And then lastly, the bootstrap circuitry, that just consists of a capacitor. The capacitor needs to be able to withstand whatever voltage you're looking at applying to the gate of the MOSFET. So for example, usually people are applying 12 to 15 volts, so a 25 volt rated cap is more than sufficient. We're going to calculate the capacitance needed in a minute. That's the whole point of the video, and that's pretty much all there is to it. What I spoke about before about having capacitors in parallel is basically it provides a better frequency response across the frequency range. So the equivalent series resistance of a capacitor sort of dependent on frequency. So if the frequency changes, the ESR may change. And the best thing that we can do is if we parallel different types and different sizes of capacitors, it will give us a much better frequency response. The ESR will be lower across a larger frequency range. Basically, I probably will draw this wrong now, but if we plot frequency here and ESR over here, you've got sort of different curves, and putting them all together gives you the lowest response possible. I may do a separate video on this, but there's plenty of them about, so feel free to have a look. But the main thing to take away from this is that every capacitor has an equivalent series resistance. If we parallel capacitors up, it's the same. If we take their ESRs, we're paralleling the ESRs up, and the overall resistance of these two is going to be less than what they currently are at. So it's always good to do that. So I recommend having an electrolytic capacitor for the bulk of your capacitance, and then a small ceramic there just to knock down the ESR. And finally, so that's the capacitors. The only other thing left really is the diode. Now, the diode needs to be able to withstand the full voltage seen across the load. So if you're switching 300 volts, then you need to make sure that your diode is rated for blocking 300 volts. And the other thing you need to consider is the current through the diode. Now that's going to be a product of the frequency, and so if I say I max through the diode is a product of the frequency, so mine's 150 kilohertz, and a value called the total charge, and that's the total charge needed in order to turn a MOSFET on. This is usually in the order of nanocoulombs, but we'll get to that in a moment. But that's the equation you would need to look at. Very simple equation for the diode. Okay, so make sure that's on screen like that. Okay, the equation that we're going to be working with today looks quite complicated, but it's this one. Now, it looks very complicated and very long, but basically the equation is derived from, and if anybody needs it derived, I can do so, but for the time being, let's just state it as this. It's derived from the Q equals CV equation. So for a given voltage and a given capacitance, we'll provide a certain amount of charge. So if we need to know basically what we're trying to do with these capacitors is provide enough charge at a given frequency to ensure that we're always above the minimum voltage required to turn the MOSFET on. So we're looking at the minimum voltage required to turn a MOSFET on. We're looking to take the worst case scenario, the maximum amount of charge that we will need to provide, and then we're just left with the capacitance that we need for that. And so if we rearrange this, we get Q max over V min is equal to a certain amount of capacitance. Okay, so if we just take the parameters out of this, and I can explain them as I go along. Qg is the total gate charge needed for the IGBTs that I'm using. That's 75 nanocoulombs. IQBS, this is the leakage or I think it's the quiescent bootstrap capacitor current, which is an attribute associated to the IR2110, so you can look that up in the datasheet, which is 230 microamps. QLS, this is the level shifting charge required. Again, that's an attribute of your driver, so it's typically 5 nanocoulombs for sort of a 5 to 600 voltage gate driver. And then we've got ICBS, and this is the leakage current of your bootstrap capacitors. So I don't have a data sheet for the capacitors that I've used because I've just got them out of my junk bin. If you're using only ceramic, which there's nothing wrong with that, if you can make up enough capacitance with just ceramic resistors, do so, it would be much better. But if you're using electrolytics at all, then they do have an amount of leakage. I'm going to say 200 nanoamps for mine, just as a generic value. Then we have VCC, which in my case is going to be 12 volts. Then we have the forward voltage drop of your diode. So once you've found your diode, you can check the data sheet and see how much voltage drop is across the diode, because of course in here the bootstrap capacitors are going to be charged up to VCC minus your drop across the capacitor there, also across the diode. Also there will be a voltage drop across the load, and you need to take away the minimum amount of voltage required so that we get basically a minimum overall here. Okay, VLS is the next one to look at. So this is, like I'm saying, this is the drop across your... Okay, sorry about that, my camera battery died, but let's get on with it. So VLS is the drop across your load or low side switch. For a MOSFET, that's the RDS on that I was talking about multiplied by the current, or for a IGBT, which is what I'm using at the moment. By the way, IGBT, this is an insulated gate bipolar junction transistor. I like to think of them as a sort of a switch with a MOSFET front end, so you interface to it like it's a MOSFET, but it has all the current sort of characteristics of a bipolar junction transistor. If you're using an IGBT, then your VLS is given, usually there's a graph in the datasheet, and it's a graph of the current through IDS, through the drain to source, and then you've got VCE, which is essentially your voltage drop across the collector emitter. They use the same terminology as a BJT, and you'll have some, I don't know what the graphs look like now, I can't remember. You'll have some curves like this. Basically, you go along what the amount of current you're going to be drawing is, and you come down and you get a value there. So for me, that's 1.5 volts. So they're quite a large drop across there. Finally, Vmin. Again, you'll get this from the data sheet of your switch. So this is the minimum amount of voltage needed to turn your switch on, and mine is 4 volts. If we put all of these into the equation above, so if we put all of these parameters into there, we get a capacitance value that needs to be greater than or equal to, because remember this is the minimum amount of capacitance needed, of 57 nanofarads. Okay, as a rule of thumb, I times this by 15, and that gives me 850 nanofarads of capacitance, and that's a very big safety margin. But with capacitors, you get terrible tolerances with them. They're dependent on temperature and stuff like that. So multiplying by 15 is a good safety margin. And now we can look at the current rating of the diode. That's the gate capacitance, or total gate charge, times by the frequency. And in my case, that's a total of 11.25 milliamps. So I need to make sure that my diode is capable of passing 11.25 milliamps, and also that it's able to block VCC, which it will be, because my VCC is about 12 volts, and most diodes are going to be able to block 12 volts at 11.25 milliamps. So no worries there. If anyone's interested, the diode that I'm using is one that everybody's used, I'm sure. It's the UF4007. You can find them pretty much anywhere. It's just one that I had laying around, and that was the one that I went with. Okay, so I'll just do a brief talk about the circuit that I have here. So I'm using the myDAQ to supply the digital I/O for it, to turn it on and off. So this is the high side controller, or high side control input, low side control input. Here's my high side switch, my low side switch. I have a buzzer which is imitating the coil at the moment, because I don't want to be driving a coil. I'm waiting for wire to come in at the moment to finish making the Tesla coil, which is why I'm doing this video now instead of a Tesla coil video. I'm using two 220 microfarad capacitors. Those are acting as a voltage divider, so that I've got VCC over 2 here, which then allows me to drive, if this switch is on, then I'm going to have current flow through here, and if this switch is off and this one is on, then I'll have current flow through here. And what it allows me to do is to drive on one cycle, if you like, a positive here, and then on the next cycle a positive here, and that gives me a nice switching waveform, which for the Tesla coil is beneficial because it's going between plus and minus. So we're doing something like this. This is beneficial for a Tesla coil because the average of this and the average of that, your RMS, is essentially 0, which means that ideally you're switching, you have less switching losses and less power dissipated in these two switches, which is also obviously very good. There's my bootstrap diode there. As I said before, he's charging these caps up. I've got the 2 capacitors that I mentioned. The first one is 1 microfarad, the next one's 10 nanofarad. I've probably drawn these the wrong way around. It would be better to put the 10 nanofarad as close as possible. H out connects to the gate of the high side, LO connects to, or low out connects to the low side switch gate. COM and VSS are tied together. If you were designing a PCB, you probably wouldn't do that quite like this. You would have, I'm sure, separate ground planes for your logic levels as opposed to your power levels. It's always good PCB design practice. So, but for the time being, this is on a breadboard, so I don't really care. I've just tied the two together to ground. VDD is your logic supply voltage, so 5 volts, that's coming from my myDAQ. And SD, this is what's actually going to allow us to play music with the Tesla Coil later on. So SD is the shutdown pin. And a little bit of information about a Tesla Coil is that they run at quite high frequencies, so in the range of 50 kilohertz all the way up to 1 megahertz. And here it is working. It's a rather annoying noise, but that's the buzzer switching at approximately 1 kilohertz. Sorry, that's the maximum that the myDAQ can do. It uses if you're interested, it uses the PC's millisecond counter, and so 1 millisecond is the smallest resolution that you can get. So the reciprocal of 1 millisecond is 1 kilohertz. You'll notice that if anything happens on the PC, then it will stop refreshing, or the scheduler will stop working with the myDAQ quite so much, and that means that you do get lag. So if I do something that causes this to become laggy, there you go. You can almost hear how often it's being attended to by the scheduler, because it's got that repetitive lag to it. Okay, so what I'm going to do is, although I don't have an oscilloscope, this can be used as an oscilloscope, so I will try and show a few waveforms now. They won't be of any good resolution. I am looking to get an oscilloscope, so just bear with me. Okay, so this, just so you know, that this is implemented with the National Instruments myDAQ. It's really quite slow, 12.5 kilosamples per second. It doesn't help that I'm running LabVIEW in the background. This can go up to usually 200 kilosamples per second, which is okay, depending on the applications you're doing. Like I said, I really am looking to get an actual oscilloscope. But just so we can see some of the type of waveforms that we've got going on here, this is the, let's have a look. So this is the drive to the buzzer at the moment, or what the Tesla Coil will be driving it. That's coming straight from the high side driver. So you can see that's the gate charge there, the gate voltage there. We're getting about 10 or 11 volts. This will be one diode drop below VCC because of our bootstrap diode. So that's important to remember. And I can take this out and we can plug it into, let's have a look, the low side signal. So this is what's coming from the myDAQ to the IR2110. See, it's a lot lower. Unfortunately, we don't have the resolution with this to see any turn on times. I can trigger it on an edge trigger. Put that up maybe. So there we go. It's triggering very badly, unfortunately. Let's do a single shot, the equivalent of a single shot trigger. There it is there. We don't have the resolution, unfortunately, to look at any type of ringing that we may be getting on there. It just appears as a solid straight line, so you miss all of the sort of information you would need there, because of course if I'm going to be driving this with a Tesla coil, I will want to be limiting the amount of current available to the gate so that I don't burn out the IR2110. I don't want to be drawing, you can draw a couple of amps from this very quickly. You can damage it. So if you put a gate resistor in there, usually sort of about 5 ohms or something like that, that can help that, and it would smooth this curve out a bit, so it wouldn't be such a solid thing like this, and it would usually have some ringing on the top like that. But if we put a gate resistor in there, it will just slow the turn on time a little bit. It will get rid of this ringing. It will increase switching losses a little bit,
but it will reduce all the ringing. We'll have.
Okay, thank you guys. So that's all there is to it. Using IR2110 is really simple. So if you've got any application where you need to drive a MOSFET or something like this, and the the usual microcontroller just doesn't quite cut it, then have a look at the IR2110. Do the calculations yourself. Very simple. I've got some spreadsheets that I keep primarily for doing the calculations, so I just have to type them in every time. I have to do it by hand. Quite often I'll use the same MOSFETs if I've got some lying around, so generally the equations are the same, maybe just switching frequency that changes. So yeah, that's all there is to it. I'm waiting on some wire to come through so I can finish off my Tesla coil build. You can see here that it's pretty small. I ran out of wire halfway through. It doesn't have enough power to generate any sparks or anything, so I'm just going to decide to scrap the Slayer circuit, and I'll just go with a bigger solid state driver. And one last thing, thank you to my Instagram followers, LifeEEMax, who are following me. You guys probably saw a little bit of this just before the video comes out. Whilst I was making the circuit board, I took a picture and put it on Instagram. So please follow me on Instagram. I quite often post things that if I'm fixing a car or something like this, something outside of, something that doesn't really facilitate a video, I'll put that on Instagram, or pretty much anything else. Most things that I do go on Instagram and YouTube anyway. So yeah, please subscribe, follow me on Instagram, and hit the like button.